Let's review the ending of last time. So this is a matrix picked almost at random, a linear operator 2 by 2 picked almost at random. Well, not exactly, but and then we want to find eigenvalues, eigenvectors, eigenspaces, and based on that explain what that operator does without using anything else. Okay, so just to confirm our theory. And so we went through writing that characteristic polynomial there as the determinant, computing the determinant, putting it in the form of a quadratic polynomial, as you can see at the bottom, and then solving it using nothing but the quadratic formula. So that was not too complicated. Okay, okay. So in that way, we immediately found the two eigenvalues. But as you can see, a few things certainly came up, such as understanding of the determinants that was necessary. Then before we even found the eigenvectors, we decided to interpret the result, and the result of -3 and -2 as eigenvalues. It means that these are the two stretches of the eigenspaces. So one eigenspace that follows the first eigenvector, and it is stretched by -3. Okay. That's the picture right there. So the purple one, I'm sorry, the orange one. The orange one is that's V2. The blue one, V1. Okay. So and what happens to V1? And the whole there is a whole eigenspace there, whole line. And what happened to it? It is not going anywhere. Eigenspace did not go away. It did not turn or disappear. It was just stretched and flipped, and because it's a straight line through the origin, you do not see the effect of such an operation on that line. So that's the blue line. Okay, the same thing happened to the orange one. The second eigenvalue, second eigenvector V2, and the second eigenspace, which is once again a straight line. And what happened to that straight line? It was stretched and flipped. Okay, or flipped and stretched. Okay, so that's the classification of our linear operators. Is that under these circumstances, that's how they behave. When we have our characteristic polynomial is a special kind. Not any quadratic polynomial will produce these results. So that's to be addressed in a minute, or we tried to start last time. So that quadratic polynomial, what's so special about that quadratic polynomial? It has roots, and they're different. So it is not doesn't sound like a lot. It is a quadratic polynomial, so which means that like middle school or something, but it actually has profound consequences. So once again, it has to have roots. It has to have two distinct roots. And that's then the picture is pretty much what you see here. So it will be two distinct roots. It means that there will be one direction at which there's a stretch and maybe flip too, and there is another distinct direction at which it will be flip and stretch too. Okay. Under all other circumstances, it will be different. For example, if the two roots are the same, the picture will be different. The two roots, the two eigenvalues are the same. It might be, for example, just a uniform stretch, which is very different analysis. So uniform stretch in all directions simultaneously. Nothing is happening between those two vectors. Between those two vectors, meaning the fanning. Speaking of the fanning, what are you doing here? This is the fan. What's happening between two eigenvalues? And well, I will just spend a couple of minutes trying to make a fan to the best of my ability. Fan. Okay, so once again, this is the picture right there. So you start with a fan, and the edges are you usually fan. They're made of some kind of a rigid ends. This is kind of soft, more or less, or at least flexible, and you have two rigid ends. Okay, and then you open it to some degree. Depends on the circumstances. So suppose this is open. That's the original state, and then whatever happens under the operator, as you can see, nothing much. In that particular case, it flipped it, but the flip itself is really not that important. It is imagine that there is no flip. Then what's going to happen is these two eigenvectors at the ends will be stretched at a different rate. for example, one may be stretched and the other is not altogether. Then what's going to happen is, imagine that this one, imagine how could I try? Imagine that there's a nail here, and there's a nail there. So it's nailed like this. If this edge is nailed altogether, but this one I am able to pull. Okay, then what's going to happen is these vectors in between, they will not be uniformly moving in that direction. No, they will be pulled rather towards this eigenvalue because it's getting longer. So this will be put as you move from right to left. This will be slightly stretched. This is more stretch, more stretch, more stretch, and altogether they all also have some inevitable rotation. Okay, so that's what's happening when the two eigenvalues are distinct. And then there is a third possibility. So distinct, same, uniform stretch, and the third is there are no eigenvalues. So that's still to be discussed. But let's finish this example quickly. So then we had to do go back straight to the definition. This is the definition of the eigenvector. So knowing the eigenvalue, we plug it in. So as you can see, A multiplied by V1 is equal to negative 3V1. That's the equation to be solved with respect to x and y. Every time we do that under these circumstances, we end up with two equations, identical equations, which means that there will be one equation, two variables, which means that we're not going to end up with a one number, but rather with a whole line. Okay, and that's what happened. We discovered the two eigen vectors and two eigenspaces of these two eigenvalues, and both of them are straight line. One is x equal y, this one, and this is y equal x over 2, the orange one. Okay, so and then we know that once again there will be stretching in those two directions, and in between there will be fanning. Okay, so that pattern will continue on. This is where fanning is coming from. The vectors between V1 V2, and now in the n-dimensional case, what comes into play is the fundamental theorem of algebra. This is two-dimensional case, has been up to now, and then will have at most n real roots, counting the multiplicities. If you are prepared to deal with complex numbers, it has exactly n complex roots, but since we certainly not going to no time for any complex analysis of complex situations, so we're going to try to figure out what to do with that when there are no roots. Okay, so the situation that started over here, a rotation through 90 degrees has produced a quadratic polynomial that has no roots. Okay, so no roots, no eigenvalues. Okay, real eigenvalues, and therefore, what does it mean? It means that no vector is stretched. That was a typo. Okay, so let's make sure that we understand. So we have been looking for any and all eigenvalues, and as we define them, and the method for finding them, one and only, is this with the characteristic polynomial, and we realize then there is no such thing. So this equation, lambda squared plus 1 is equal to 0, does not have any solution. So I have to try to altogether avoid it, so I decide not to worry about complex numbers, for now, at least, and just speak of as if there are no eigenvalues. There are no eigenvalues. So, which means that there are no eigenvectors, there are no eigenspaces. Which means that there is no vector is stretched in that plain sense. So what there is not happening is this. So say V and say 2V. So this cannot happen. This cannot happen. No vector is purely stretched. It could be stretched combined with something. And now we know what that something is. It's rotation. So in this situation, it is the case 3. So once again, case 1, 2 distinct roots. Case 2, same root. And third, no roots of the characteristic polynomial. So in the case 3, no roots, we know now what's going to be happening. It will be happening 2 things: rotation plus stretch. So it is connection is somewhat tenuous, but that's the conclusion that we would draw if we had go through the whole analysis. Is that once again in the quadratic in the 2 by 2 situation, so the transformation, linear transformation of the plane, then when there are no eigenvalues, real eigenvalues, we conclude that there must be rotation and also possibly a stretch. Okay, just what we need to figure out is how can we determine them from this formula. So we pretty much stop there, right? Lambda squared plus 1 is equal to 0. We stop there. There are no solutions. Can we still find any information about this linear operator? Because we would like to find these parameters. So remember, case number 1, the 2 distinct roots, 2 eigenvalues, tell us what's happening. 2 stretches in 2 directions. Okay, so it was informative. Here we know what's going to be happening. There will be rotation and stretch. So what is the angle of the rotation, and what is the stretch? Okay, so you can certainly guess it from here. We started with the 90 degrees rotation, and it is not entirely. It's certainly not entirely obvious, I guess, to figure out how to figure out the angle from the matrix itself. The angle as well as the stretch from the matrix itself. Let's start with this analysis to move in that direction. Let me add in one more. So example ends here. This is our 3 cases. Okay, 3 cases. And so the analysis is fine as far as this example is concerned. But we already knew what that was to begin with. So that was not very helpful if you already know the answer. So we discovered that the rotation 90 degrees, we didn't even make a connection from the 90 degrees that we started with to the matrix. If we look at our matrix, where does it say that we have a rotation of 90 degrees? So let's make it slightly more general. Let's make it slightly more general. Not slightly, but let's go all the way general. And by that, let's look at the rotations. So F is a rotation through angle theta. So the matrix, as you might remember, is cosine theta on the diagonal, and negative and sine and negative sign elsewhere. Okay, so I could once again I can go the same way and try to find. Let's write the characteristic polynomial. So the characteristic polynomial of this matrix of lambda is cosine theta minus lambda, cosine theta minus lambda, negative sine theta, and sine theta. And we're supposed to take the determinant of this. Okay, so just to have the characteristic polynomial and try to connect, by looking at the characteristic polynomial, try to identify what theta might be, how theta might be appearing there. So, okay, so it will be cosine theta minus lambda squared plus sine squared theta, right? Yeah. Okay. So if we simplify, what do we get? We have a cosine squared theta minus 2 lambda cosine theta plus lambda squared plus sine squared theta. Okay? Let me rearrange the terms to put it in the standard form. So this is what we have. Cosine theta, lambda squared minus 2 lambda cosine theta. And the last term is sine squared plus cosine squared, which is 1. Okay, trigonometry, remember? So that is our polynomial. The characteristic polynomial of rotation is this. Okay, so the angle is explicitly present. On the other hand, there is a 1 present. What is the importance of 1? It is in fact the stretch, or at least that's the guess that we make for the time being. It is a pure rotation, so it's not rotation with, it is pure rotation like this. So there is no stretching. So if we are looking in the characteristic polynomial to identify where the stretch is hidden, and turns out it's hidden in plain view. That 1 over there, the last coefficient that is present in the characteristic polynomial, the free term, turns out to be the coefficient of stretch. Okay, so we're multiplying by a number. You can see why this is the case if let's just leave it at that. And okay, so that's the stretch, and this is the angle. Okay, so you're gonna have every time you're gonna have the when you have an equation like that, you know it's gonna be a rotation. So, for example, if I have imagine hypothetically you have lambda squared minus say plus p lambda plus q. So suppose this is our characteristic polynomial of lambda. Okay, so from this we can figure out whether or not it is a rotation. So rotation, this is a rotation when q is equal to 1. But well, actually that's the second condition. What is the second condition? What's the first condition is that no solutions, no roots rather. No roots, right? Because if there are roots, we know what it is. There's a stretching, there is no rotation. That the case we started with has no rotation. Fan, right? So a fan that actually keeps those 2 ends of the fan intact with some turning of the vectors in between, but otherwise there is no rotation. That is a rotation of the whole plane, with possible stretch. And that is why we have to eliminate that possibility of that simple situation we started with. So rotation when q is equal to 1, but number 1 to be verified is no roots, and then this is okay. So when do we have no roots? A quadratic polynomial has no roots. When? I guess we have to spend some time on that.
Well, it would have no roots when it's an even degree.
It is even degree. The degree is 2.
Right, and when it is concave up and positive at the apex, or concave down and negative at the
Well, you're thinking calculus, but this is there is a very precise answer to this question.
There was a formula?
Yes. Quadratic formula.
If it's less than 0?
Yes. What is less than 0?
Like the thing, like the triangle? Not the...
Oh, the root.
B squared minus.
what's the word for it? Quadratic formula is negative p plus or minus square root of p squared minus 4q over 2. When this is negative, there is no root. But what is called denoted by d, which stands for what?
No.
Not the determinant, not the denominator, close. The determinant determines. Okay, and this one, what does it do? It discriminates.
It's screaming up.
Yes. It discriminates between these two major cases, whether there are no roots. So positive, d positive, 2 roots, d is equal to 0, 1 root, and d less than 0, no roots. Okay. So so that's that. Every time we have then a polynomial, we already have this very simple. Every time we have a linear operator, this is a very simple way of telling whether or not there are roots, and therefore we can tell without doing any other work. We can tell whether or not this is rotation, if there is a rotation. So so this is how we proceed then. These 3 cases that we just discussed. 2 roots is, well, let's call it fanning. I can think of a better way to describe it. So the 2 vectors preserved and stretched only, but separate direction. D equal to 0, it is a pure, let's say, scaling. Scaling because the whole thing is scaled uniformly. And negative is rotation. So rotation is still might come with stretching. So it's easy. You know, if there is a pure rotation, how do I add scaling or stretching to it? I just multiply it. So for example, like this. Over there, it is a rotation with stretching by a factor of 2, right? So the same matrix with sine cosine, and if everything is multiplied by 2, every term inside of that matrix, we will have a rotation with a stretch. So it's straightforward if you know what the answer is. The question is, what if there isn't? What if you're starting with a matrix that is unfamiliar? Okay. Okay, so this is these are the 3 cases, and that will produce our classification of what can linear operator can possibly do, and these are the 3 things: fanning between 2 eigenspaces, uniform scaling, or rotation combined with a stretch, uniform stretch once again. So rotation and scaling. So sometimes I prefer to use the word scaling rather than stretching, so to emphasize the point that it is you scale the whole thing, not one vector or one eigenspace at a time, which is what case 1 is about. So let's do a little bit more analysis here, and so we can look at this situation in a slightly more direct way. Okay, so we have A, B, C, D is our matrix. Okay, and then we are looking at its characteristic polynomial as the determinant of, once again, A minus lambda, D minus lambda, B and C over here. Which gives me A minus lambda, D minus lambda, minus BC. And we can simplify this. That's the good thing about it. So I'll have AD minus D lambda minus a lambda plus lambda squared minus bc. Okay, so it will be lambda squared minus a plus d lambda. And what we're left with is plus AD minus BC. As you can see, the leading coefficient is 1, so that makes our life easier. The last term we should be able to recognize. It is the determinant. And this one is also not unfamiliar. A plus D. You remember what we call it? A plus D, two diagonal elements added together. Remember the name for it? It's called the trace. And so that's turns out that our characteristic polynomial is expressed in terms of two very specific characteristics of the original matrix. Okay, so once again, the trace, the two elements added together, and the determinant. We already have some ideas of the meaning of these two based on examples, right? So for example, let's look at the determinant for different linear transformations. So, well, one is, so A is rotation. What is the determinant? Go backwards. Look at that matrix at the top. What's the determinant? Can you quickly compute it? It is 1. That's right. So that is tell. So right away the matrix would have to. That doesn't tell you everything else. You see there are extra restrictions, but at the very least it gives us the determinant equal to 1. It does not tell us that it is a rotation. It goes only this way. If it is a rotation, the determinant is equal to 1. You can easily think of a matrix that is not a rotation, and yet it is determinant equal to 1. Say 1, 1. Okay, so or anything like that, or say 1/2 and 2. Okay, so there are matrices that are not rotations. What determines the rotation is what I just mentioned. Is what is actually, you want to go backwards. What tells us that it is a rotation, and that is told by the discriminant. Discriminant less than equal to 0 tells us that it is in fact a rotation. Rotation plus a stretch, possibly. So let's see what the determinant is. It's also an expression here. We can deduce it from this. So remember, it is well. Let me write it out. Probably in shorter terms. So lambda squared minus plus p lambda plus q. Okay, so that is my quadratic polynomial, and its determinant, discriminant, is equal to p squared minus 4q. That is the discriminant, and then the transitional case. Discriminant equal to 0 is the transitional case between positive and negative, between 0 and 2 roots. It's remember that once again, that parabola that goes up and down, and if it goes down, it touches the x-axis, creating a root, and then it crosses and it becomes 2 roots. Okay, so that's a transitional case. Where's that picture that I had? Here it is. The transitional case. So you're imagining like this. Well, actually, it moves moving up. Okay, so you have a parabola moving up, which all it takes is to change the last term in that quadratic equation, which would pull the parabola up and down. And so if you keep pulling it up, then if you have 2 roots, at some point you'll have 1. But it is a transition. It is like not a long transition. It is an instantaneous transition between 2 cases, right? So you have for a while you have 2 roots, and then suddenly you have 1, and once you passed it, and the next moment you have none. Okay, so it's transition. It's like a border between 2 countries. Okay, so so in that transitional case, is d is equal to 0, and you can actually ask yourself what is that the nature of that transition, and it is happening when p squared is equal to 4q, okay, or it is, what is it? Our trace is equal to 4 times the determinant of the matrix. Okay, so that's when, that is the special case when the trace of the matrix is equal to 4 times the determinant. It is where when we transition from these two different behaviors, rotation stretch or fanning and stretch. Okay, so okay, so okay, so where is the okay, so determinant is equal to 1. So if we are if you are given, so starting at the very end, and suppose you started, suppose where this is where we are, suppose this is a starting point. You have some numbers. You have some numbers here and there. Okay, and examining those two numbers should be sufficient for us to tell what this thing is. So you look at the discriminant, right, of this p squared minus 4q. If it's negative, positive, and negative, you already have classified things sufficiently, right? So once again, given characteristic polynomial, before looking for lambdas, or as you look for lambdas, doesn't matter, you look first at the determinant. So you move to the determinant, which is once again p squared minus 4q, which is trace, what is it, trace squared, yes, trace squared minus 4q for a determinant. Okay, so then, and then 3 cases. D is positive, D is negative, D is 0, D is negative, and once again we know what these are, so I'm not going to list these 3 possibilities. It is not a sufficient, it is actually pretty impressive accomplishment already. So you know what the polynomial, the linear operator is doing. What is missing is that would be the next stage of analysis, is to find out particular situations, particulars of the transformation. So we know case 1 will be fanning, but you still need to find the factors and the directions. So that's what we already done. Then the very first example today was exactly that. The discriminant was positive. That is why we had 2 roots. Okay. Then from those 2 roots were the factors, of stretching factors, and then we found the directions. Well, we found it last time, but we just pointed them out. Okay. So discriminant is equal to 0. It is a special case. So, well, it will be something much simpler. So it is a stretch of some kind. So I'm skipping that for the time being, and now the case that we need to concentrate on is the last one. We know that it is rotation and stretch, and then once again, what do we need to find? We need to find the factors of the stretch and the angle. Okay, so once again, from these numbers, we have to find the angle. It is not really so let me just give you the answer so we don't have to spend too much time on that. So once again, our interest is case 3 right now, case 3. And we're trying to do it without complex numbers. So that's a bit of a challenge, but that's okay. Okay, so I have, okay, so not the factors, I'm sorry, that's kind of a crucial mistake I made. The factor 1, that's the difference between case 1 and case 3, 2 different stretches along 2 different directions. That's case 1. Case 3 is 1 stretch in all directions, uniformly scaled. Okay, so that's why I like to put it one word, rescale. Okay, so one factor, what is that factor? The factor is in fact, well, it is a bit surprising. It is actually the square root of the determinant. Square root of the determinant. So that is why we already guessed that. Remember when we talked about pure rotation, we discovered that the determinant is equal to 1, and that's we know that that in that case there is no rescaling. Okay. Why is a determinant? What does determinant or square root of the determinant have to do? Can possibly have to do with rescaling? And it's not entirely it's far-fetched. To begin with, it actually supplies. Think about units. Think about units. So we're transforming. That is our linear operator. We're transforming the plane. Everything is measured in feet. Okay. Then the numbers are they are measured in feet. And then if you all of these feet, so you multiply feet by feet, you have feet squared. Then you take a root, and you have a feet again. Okay. Yeah. Well, let me give a better example maybe. How about the determinant of this matrix? This one. So you remember what this matrix is. This matrix, it does the... No, let's make it 3 and 3. What this matrix does, what does this matrix do? Right, so if we compute that's right, so it is uniform stretch by 3, so if we compute the determinant, it will be 3 squared, and if we have also the square root there, we'll have 3. Okay, so that works out, right, as you think. If it is non-uniform stretch, then it is slightly more complicated, but you can still make a case that, well, let me pick some number. Okay. 2 and 8. How about 2 and 8? Yeah. Okay, 2 and 8. The determinant is naturally 16, and the square root is equal to 4. Okay, so the determinant, that is linear algebra is well, we just didn't have the time to discuss it, but the determinant is the area of the a parallelogram formed by the two vectors for the basis vectors. So wherever the two basis vectors go, they form a parallelogram, and the area gives us the determinant. So which means that if everything is stretched by 2, that parallelogram will increase in size by 4. Okay, so but if you want to only tell that number where is 2, well, you take a square root. So if the area is increased by 4, it means that in all dimensions, at least on average, the stretch is by a factor of 2. So that's the last example I tried to suggest. What if the stretch is non-uniform? So 2 in one direction and 8 in the other direction. Okay, so it is a non-uniform stretch, but if you want to speak in terms of areas, they will be stretched by the factor of 16, which means that on average, the directional stretches will be by 4. It makes sense, right? If you stretch it horizontal is by factor of 2, vertically by a factor of 8. Of course, one way to try to figure out what the average is to take the average literally, 2 plus 8, and it will be 5. But it turns out that's not the best way to do it. The best way is to look at what's happening to the areas, and the areas increase by the factor of 16. Which means that on average the length increased by a factor of 4, square root of 16. Okay, so indeed the determinant is responsible for changes of the dimensions of the plane. In fact, if anybody took calculus 3, you might remember that that number appears in double integration formula. Anyone who has taken calculus 3? Well, it is when you change variables in a double integral, then you have to have an extra term that corrects that substitution, and that so that you would not over calculate your volume. So you have to divide or multiply by that factor. Okay, so the second missing part is the angle, and we can also find it here. We kind of already know what it is. It has something to do with the trace. When q is equal to 1, then we know what the answer is right here. When q is equal to 1, the simple case of rotation, pure rotation, we have then where is my so this over here, -2 cosine theta, that is my p. Okay, so when q is equal to 1, we can find theta by doing our cosine, right? So it's very similar, except both p and q will be appearing here. So that's all. So let me just write the answer. So the angle is so it will be arc. Why do I have arc sine here and not arc cosine? Well, arc sine, arc cosine, same thing. I mean, sine and cosine so interrelated that you can have formulas expressed in terms of sine or cosine very pretty much the same way. So the answer that I have here is theta is arc sine. Do I have to explain what arc sine is?
What?
Arc sine? It is the inverse of sine. Right, so we talked about inverses, so once again it comes very handy that discussion. So our function has the inverse whenever it is 1-to-1 onto, which sine is not. So that's something to be that you need to know, that you have to cut the domain of sine in order to make it into a 1-to-1 onto function, and only that way you're going to have bijection. Okay, so this is my sine, y equals sine x, and it is not 1-to-1 nor onto, so, well, at least you need a 1-to-1, right? So it fails the horizontal line test, which means that I have to cut it. You see how I cut it to turn it into a 1-to-1 function? Right, one cycle, and usually it is taken from here to there. Right, so that is a perfectly all right bijection, and it satisfies the horizontal line test, and we have the inverse. It has the inverse, and so we can use it freely to find the angle that we're looking for. So this is the formula: 1/2 p squared, which is what is my p? P is my trace squared over the determinant minus 4. Well, kind of complicated formula. Let's verify it at least. Make sure that that we have it. We did it right. So.
Is that inverse sine of that whole expression?
No, it's like F inverse. It is the inverse. It doesn't stand for power. It stands for the inverse. So sine inverse is arc sine. So alternatively, arc sine. That's what it stands for.
Yeah,
so
like that whole following expression, like that 1/2.
Let me make it clear like this.
Yeah. Okay.
Yeah. So put it in parentheses. So, all right, so if there is no okay, so let's confirm for rotation. So if this is rotation through theta, then we know the determinant is equal to 1, okay? And the trace is, what is the trace? 2 cosine, right? The trace is 2 cosine, so it will be 2 cosine theta squared minus 4, 1/2 arc sine, okay? So, I'm sorry, I missed the square root over here. Okay, so what does it produce? Arc sine of 4 cosine squared minus 1. Why do I have the wrong direction? Cosine theta. The sign, I messed up the sign, I'm sorry about it. So the sign is the opposite sign over here. So this is plus and this is minus, otherwise it's not working out. So so if I have minus sign here, then I could pull, this is 1/2, I will have sine, I'm afraid I'm running out of time, but it does work out just fine, square root of 1 minus cosine squared theta, which is sine squared theta, right? Sine inverse square root of sine squared theta. And as you can see, it works out. This is theta. Okay, just the sign. We'll have to review this next time just to make sure that we got it straight. Okay, so try to think about